Yeah.
So what were we doing using matrix calculus was,
Yeah.
we were setting this equal to 0 and then we were saying this is either a point of minima
The empirical loss function.
or a point of maxima. Fine. How are we saying this? What are these derivatives called first of all? What is this kind of derivative called?
Partial.
Okay, wait, let us have a look at this. So say we have a function f of x and to find its del x f, what do we do? The procedure of finding?
F of x plus
F of x. So
x minus
we do something like this. Wait. So we do f of x plus dx minus f of x, and this we call it df. What do we do after this? We write it as some dx transpose times v, and this v is del
of f.
Fine. This is what was the procedure I described. So this was the procedure described for doing this. Fine. Now let us try to understand what this thing is called. What is this called? Okay, before that, before what is this called? Let us see this definition. Limit norm h tends to 0, f of x plus h minus f of x minus v transpose h by norm h. If this is equivalent to 0, then v is called the Frechet derivative of f. See, if you have a limit satisfying this, if there is a v satisfying this limit, if there is a v which is satisfying this limit, suppose that there existed a v which satisfied this limit. Okay. Suppose that there existed a v which satisfied this limit. We do not know if that exists or not. Now suppose I have something like this, some f of h by h, limit h tends to 0 is equal to 0. How do we write this in small o notation? We write this as small o, f of h is small o of h.
This is going out of focus now.
Now? So do you get this?
Okay.
Small o notation. This means that this f of h will grow slower than h, whatever be this, with some constant. This is what it means, right? So, if I have this, can I write f of h? Okay, fine. So let me now come to this.
Okay, wait. 1 second. Hello.
Yeah.
Hello. So small of h means that fh will grow slower than h.
Yeah. That is when this happens, no? Oh, sorry. fh will grow a bit faster than h.
Faster than h.
fh will grow a bit faster than h. Slightly faster than h. That is when this will become 0, no?
Yeah.
Okay. So, because this is h tending to 0. Okay. Fine. Okay. You leave this. Just this is the definition of small o.
Yeah, this
One of the definitions of small o. F of h is small o of h if limit h tends to 0, f of h by h is 0. Fine. That means, yeah, if you take it this way, this is your h for h. If your f of h is something like this, after a certain time, if it is something like this, as this, as it is tending towards 0, as you are going towards this, in this region, the graph is, the second graph is very small compared to the first graph. That is why this is happening. Fine. So that is what definition of small o of h is. Okay, at some point, after some point, say this is some h naught, after h naught, but this is around 0, not infinity. We usually use asymptotic notation in computer science, but here we use simple near 0. Okay, fine. So let us get back to this definition. This is the definition of Fresher derivative. Fresher derivative, there, which is limit norm h tends to 0, f of x plus h minus f of x minus v transpose h by h is equal to 0 by norm h. Okay, now this h tending to norm h tending to 0, f of x plus h minus f of x can also be seen as an infinitesimal increment in x minus x. Fine.
Wait. Right.
So this is equivalently seen as your TF.
Yes.
Fine. Now let us look at a two variable function f of x1 x2, and then write this f of x1 plus dx1 comma x2 plus dx2 minus f of x1 comma x2 is your TF for R2 case. Now this is f of x1 plus dx1 comma x2 plus dx2 minus f of x1 plus dx1 comma x2 plus f of x1 plus dx1 comma x2 minus f of x1 comma x2.
Wait. Okay, just
adding and subtracting this. Now this is f of x1 plus dx1 comma x2 plus dx2 minus f of x1 plus dx1 comma x2 by dx2 into dx2 plus f of x1 plus dx1 comma x2 minus f of x1 comma x2 by dx1 into dx1. Fine. Or instead you can write deltas instead of d's.
Okay.
Writing deltas would make much sense. Where delta x and delta these where these tend to 0. Where delta x1 tends to 0 and delta x2 tends to 0. Fine. Clear?
What we did before, right?
This is your DF. Isn't it?
Yes.
Now, each of this is f of x1 plus del x, x1 plus del x1, comma x2 plus del x2 minus f of x1 plus del x1 minus x2 by del x2 into del x2, where limit delta x1 tends to 0 delta x2 tends to 0 is,
delta x.
see this is tending to 0, so you can make this 0. Similarly you can make this 0.
Yeah.
So this will be f of x1 comma x2 plus del x2 minus f of x1 minus x1 comma x okay comma x2 by del x2 times del x2.
हमें कुछ दिख नहीं रहा है.
Do you see this?
I can't see the first line. First line I can't see.
This is just a repetition of this first term.
Okay.
This term has been repeated. Now you see this. What we did was, we took del x1 0 because del x1 was tending to 0. We took del x1 to 0 and then del x1 to 0 here. So what happened effectively was f of x1 comma x2 plus del x2 minus f of x1 comma x2.
Okay.
Fine. So this is your partial of f with respect to x2 times dx2. Fine.
X2.
So you can show that the second term is del f by del x1 times dx1. Fine.
Yes.
So df will be del f by del x1 times dx1 plus del f by del x2 times dx2. This was for f from R2 to R. But if I wanted f from Rn to R, df would be del f by del x1 dx1 plus del f by del x2 dx2 plus so on up to del f by del xn dxn. Fine. Is it okay? Now df will be del f by del x1 del f by del x2 so on to del f by del xn times dx1 dx2 so on up to dxn. Fine. But then we here said we'll write this h as dx. This h has been replaced by dx, isn't it? Fine. So this can be written as, this is the vector h. Okay. Now this we defined as some. Fine. So this is del x f transpose, this was del f transpose h. Fine. This is df, isn't it? Now once this is done, let us try to substitute this in this equation. Okay, so what do we have here? Df as f of x plus h minus f of x, which we proved as transpose h. Fine. Now limit norm h tends to 0, f of x plus h minus f of x minus v transpose h by norm h is equal to 0. This has to be. Now let us try to substitute this here. We can do that, right? Fine. Now what do you get? Limit norm h tends to 0, transpose h minus v transpose h by norm h, which is limit norm h tends to 0, What?
The second line
Ah.
goes down carefully. How
What?
write it?
What?
F of x.
In the second line? Hmm?
Second line.
Hmm.
This form, the form that you know,
Ah.
transpose is that thing.
Ah. V transpose H. This has come from the definition. I'm just writing the definition again. This is the definition of something called Fresher derivative. A V which satisfies this is called a Fresher derivative.
Okay, the V is called the difference.
V is called the Fresher derivative. Okay, so now what I did is I simply substituted this here. I just wrote this definition back and substituted this instead of that.
Okay.
So now we finally have limit norm h tends to 0 f minus v transpose h by norm h. Now this should be equal to 0. Now we need to find a v such that this is 0. Now let us see limit norm h tends to 0 del f x minus v. Let us take its norm. Times cos theta, where theta is the angle between these two.
Wait.
Hello. Do you see this?
I can't see it. It's out of focus.
Okay. Now
Go to the previous page, last line.
The previous page.
Last line.
This one.
Just zoom in. It's out of focus. Zoom in. Zoom in more. I can't see. Okay.
Okay, this I wrote it in this way.
Okay. So
fine.
Okay. I got it.
Now what I am doing is we write this again over here.
Yes.
Then limit norm h tends to 0 f minus v whole transpose h can be written as the norm of this into the norm of h times cos theta, which is the angle between them, because it is inner product. This is 0. Now cancel h transpose on h on both sides. This will become now limit h tends to 0 is immaterial now, because there is no more h. Fine. Now see, now you have two possibilities, either or. Fine. Now, but you see here, norm h tending to 0 means h can take infinitely many possibilities, because it can come in any direction. That means theta can have infinitely many possibilities. Theta, because theta is the angle. So this can never, this is not certainly 0. Not 0, because it can take any value for different values of theta. Fine. So only this should be 0, which means is equal minus v is 0. That means whenever the norm is 0, the vector is 0, which means okay. So in Cartesian coordinate systems, Cartesian coordinate systems, we have v, which is your Fresher derivative, as fine.
Okay.
Okay.
Okay. Got it.
Now, if you want to have minima at a point, what do we do? Or minima or max? Okay, let us say minima at a point. You want f of or local minima. In specific, you f of x plus h, x plus say lambda h must always be lesser than or equal to, must always be greater than or equal to f of x for norm h is equal to 1 and lambda tending to 0. Do you see this?
Yes, yes, yes.
Where f is a function from Rn to R. You want this to be satisfied?
Wait, 1 second. Each can be anything, right?
H, we take it as a unit vector.
Oh, okay. In that
Unit vector in any direction. Fine. This is for all h. This should be true for all h and for some lambda tending to 0. Do you see this? This is the definition of local maxima, local minima. Then x is a local minima, or let us say x0. Then x0 is a local minima. Fine. Now, this is clear.
Fine.
Now, we have this definition of Fresher derivative, which is limit norm h tends to 0 f of x plus, here we will do this limit lambda tends to 0. We can always write it this way.
Obviously. This is a Fresher derivative.
Yeah,
Fresher derivative.
by lambda, because norm h is 1, which is actually norm h lambda h, but norm h is 1, so this will effectively reduce to lambda. Fine. So this is effectively lambda. Clear? Now, what will happen here? We know that we are in coordinates, this coordinate, so v is this. Do you see that?
Right.
Now, you can always write this upper. Now we have that this is 0.
This is for R case, right?
This is 0. So we have that this upper thing is small o of lambda, because you see the definition of small o is this.
Yeah.
Okay.
Yeah.
The definition of small o is this. So what you have is so we want to somehow make use of this. So that is f of x plus lambda h minus f of x plus v transpose h by lambda. I just cancel this lambda here, is equal to 0 for limit lambda tends to 0. Fine.
Okay.
So this is limit lambda tends to 0 f of x plus lambda h. Now x plus lambda h minus f of x by lambda is equal to minus v transpose h. Fine. And this is possible for
Yeah. Right.
all H, isn't it?
Right, right. One thing. So
Yeah.
this is for R2 system, right? This is whatever we are doing is for R2.
No, it's for Rn. See, we haven't assumed anything from R2 here. It's an Rn.
Fine, fine.
Fine. Now, so you have this. Now you know that this is always greater than that. This is always greater. If x is a if x0 is a local minima, what do you have? Limit lambda tends to 0, f of x0 plus lambda h minus f of x0 by lambda is minus v transpose h. Fine.
Yeah.
And v is now calculated at x0. Fine. So what is that? Limit h tends to 0. Okay. Now we'll use this. That is, since this is always true, if it is a local minima, this implies f of x0 plus lambda h minus f of x0 is greater than or equal to 0. That means this quantity is always greater than or equal to 0.
Yeah.
Right. That means this quantity is always greater than or equal to, because lambda is always greater than 0. We take lambda greater than 0. Fine. It is approaching from the right. It is only approaching from the right because h will take care of the direction. Because it is for all possible h will take care of all the directions. Do you see that? See, h will take care of all the directions possible. Lambda will just scale it to a very small quantity. So that is why this is all. Since lambda is always greater than 0, this is always greater than 0. That means v transpose h is always greater than or equal to 0 for all h, or minus v transpose h is always greater than or equal to for all h. And v is calculated at x star or x0. Fine. So v is del of x calculated at x0. Fine. So what is this? Del of f of x calculated at x0, or we write it as del of x0 transpose h is always lesser than 0.
For R2 case.
Yes. Now if I take, now h is all possible directions, all directions, right? Fine. Now, so we have this del of f of x0 transpose h is lesser than 0. Now take h is equal to del of f of x0 by norm of f of x0. I can always take this.
Wait, one second. Take down. So it is any possible direction, right?
Okay, wait. This was a minus. Then this is a plus again. Okay, yeah, fine.
Right.
So this is plus. So yeah. So this is always greater than or equal to 0. Okay. Now h is all directions, right? Now what I will take is h is equal to del f of x0. Okay. Now I will take h as, so this was this. Now I will take h is minus del f of x0. This is a possible direction, isn't it?
Yes.
A possible direction. So that will be del f of x0 transpose del f of x0 minus of this by norm of del f of x0 is equal to 0. Fine. I just substituted this here.
Yeah, fine.
this will be del f of x0 transpose del f of x0 is equal to 0, which is del f of x0 square is equal to 0, which implies del f of x0 is equal to 0 when x0 is a minima. Fine. So this is actually a necessary condition for minima. What is this condition? Equal to 0 if this is satisfied at x0, then x0 can be, because it's only a necessary condition, not sufficient condition, can be a local minima of f of x. Fine. Do you see this?
Yes.
Now what was our del f? Now if we came to our omega, our w for the loss function L of w, we did is equal to 0. We did this. So what were we doing? We were finding minima using this Fresher derivative. Isn't it?
Yeah.
Now what we then did was we then had this we said this w L of w is this del L by del w0 del L by del w1 so on up to del L by del wn. This was how we had this, no? Here.
Yeah. Right.
Since we had this, and then we said putting this equivalent to 0 is the same as saying del L by del w0 is equal to 0, del L by del w1 is equal to 0, and so on up to del L by del wn is equal to 0. Fine.
Yes.
Now what did we have this LW as? We had this LW as I from 1 to n yi minus w transpose xi whole squared. Isn't it?
Right.
Now LW was therefore 1 by n sigma I from 1 to n yi minus w0 plus w1 x1 xi1 plus so on up to wn xin whole squared, right? And then we said let us try to only observe just this. Fine. So this was 1 by n sigma I from 1 to n 2 yi minus w0 plus w1 xi1 so on up to wn xin whole squared into 1 times 0 is equal to 0. Fine. This reduced to I from 1 to n 2 by n outside yi minus w transpose xi whole squared is not whole squared is equal to 0. And then we said this is equivalent of writing sigma I is equal to 1 to n y minus yi minus w transpose xi is equal to 0. But then w transpose xi was your yi cap. the prediction.
Yes.
Now this can be written as sigma I yi minus yi cap plus sigma I say j yj minus yj cap is equal to 0, where where we want to write this sigma I yi minus yi cap is all greater than or equal to 0, and sigma j yj minus yj cap is all lesser than 0. Say this I belong to some n and this belong to n complement, where n is
Define n inside, right?
n 1 to n and n complement, where or like n union n complement is this. N union n complement is this, where n and n complement are defined this way. This defines n, indices n, and this defines indices in n complement. Fine. Now what did we say? This was called what? Now how did we picturize this? If it was in R2, if this is the line of our predictions, which is W transpose Xi, our Y's would lie somewhere here. Fine. And then we said, if we find the sum of these lengths, and the sum of these lengths, so what did this greater than 0 represent? Sum of these black lengths. This was represented by sigma I y minus yi cap greater than 0 was all these points, and then sigma j y minus yj cap lesser than 0 was all these points. Now what do we have is the sum of these two is 0. That means the sum of these black colored lengths is equal to sum of blue colored lengths. Fine. And what did we call this upper thing as? Overestimate. Sigma I y minus yi cap I such that yi minus yi cap is greater than 0, then for all such yi minus yi cap is called the overestimate. And then we had this j such that yj minus yj cap is lesser than 0. Then we called this then we can remove this. Then such j, then for such j, yj minus yj cap is called underestimate or negative of underestimate, because this is a negative quantity, whereas estimates are lengths here. Over and underestimates are lengths. Underestimates are lengths. So we always have them to be positive. So this sigma I for yi minus yi cap plus sigma j for yj minus yj cap is equal to 0. This is called overestimation minus underestimation is equal to 0. Therefore, sum of overestimations, so therefore, the sum of overestimation in linear regression with squared laws, we have the or we can simply say have the sum of overestimated quantities is the same as the sum of underestimated quantities. Fine.
Okay.